This is 1-3, real numbers and the number line. So our objective for this lesson is to classify, graph, and compare real numbers and to find and estimate square roots. So the first thing we're going to talk about is a square root. So if we look at the algebraic example, this one right there, we can see that a number a is a square root of a number b if a squared is equal to b. So that means that if we do something like 2 squared, well, that's going to be 2 times 2, which is 4. So this number a, which 2, is a square root of this number 4. Okay, even better with this example right here, 7 is a square root of 49 because 7 squared is 49. Okay, so any number squared is a square root of a bigger number. And our essential understanding is that we can use this definition above to find the exact square roots of some non-negative numbers. That's important. Non-negative. Okay? We cannot take square roots of negative numbers in our number system, in our real number system. And I'll talk a little bit about that more later. We can approximate the square roots of other non-negative numbers, okay? And the best way to do that, we can do it mentally, or we can use something called a calculator to help us out. Our radical symbol, which looks like that guy right there, indicates a non-negative square root, also the principal root. So whenever you see this symbol right there, that always means we're going to take some sort of positive square root, all right, which we can call the principal square root. Now, the radical symbol is the piece in red. The part underneath the radical symbol is called the radicand. And when you put both of these together, we have a radical. Okay, so square roots are a type of radical. They are a square, right? So, 2, like we saw in the example back here. So that's a squared. There's other type of radicals, and I'm not sure if we'll get there in this class, but you'll definitely get that in Algebra 2. Maybe even a little geometry too. There's upper level radicals then we can learn about. We will learn about negative square roots in 1/6, and we'll talk a little bit about that then. So to start off, we start off pretty simply by simplifying square root expressions. So what is the simplified form of each expression? So basically, we just want to figure out what times itself, and that's important, what times itself gives me the thing underneath the radical. So what times itself gives me 81? Well, 9 squared. 9 times 9 is 81. So 9 is a square root of 81. Okay? We can also do it with fractions. Okay? And it's best to look at fractions as 2 separate things. Look at the top, look at the bottom. Because 9 and 16 don't reduce. Okay, so we cannot reduce those at all. But I can think of this as maybe the square root of 9 over the square root of 16, which 3 times 3 gives me 9, and 4 times 4 gives me 16. So 3 over 4, so if we took 3 over 4 squared, we would get 9 over 16. So 3 over 4 is the square root of 9 over 16. Okay, so the square root multiplied by itself is always going to be equal to the radicand, the thing underneath the root symbol. And when we see the square root symbol, we're always going to take the positive square root. Let's try a few more problems with our got it problems. Okay, so same thing. We're going to take the square root of 64. We got to figure out What times what gives me 64, which is 8? What times what gives me 25? That's 5. Well, 1 over 36, think about them again as a top and a bottom. So the numerator, if I take the square root of 1, I get 1 over the square root of 36 is 6. And again, with letter D, we have 81 over 121. 81, we've done that already, and hopefully you know that 11 times 11 is 121. Okay, so there are my 4 got it problems. So next, the square root of an integer is called a perfect square. Okay? For example, 49. The square of an integer is called a perfect square. So 49 is a perfect square because something squared equals 49. When a radicand is not a perfect square, we can estimate the square root of the radicand. Okay, so a weird picture here, right? But we're going to estimate square roots. So this right there is a lobster. I know it's hard to tell. Bad picture from your textbook. And if we look closely at its eye, we can see that it's made up of little squares. So let's read the problem. Lobster eyes are made up of tiny square regions. Under a microscope, the surface of an eye looks like graph paper. A scientist measures the area of one of the squares to be 386 square microns. What is the approximate side length of the square to the nearest micron? And you don't need to know what a micron is. It's just a very small unit of measurement. But what we do need to know is we want to find what times what gives me 386. So we want to take the square root of 386. So off the top of my head, I cannot figure that out. I could try to guess that 19 squared is going to be 361. 20 squared is 400. So I can see that it's going to be somewhere in there. Okay? The best way to do it is to use a calculator. Okay? So I have my nice scientific calculator here. I can just put in 386 and find the button for square root and press it, and we get that 386 is equal to, oh, I didn't see that, 19.64688. And depending on the type of question is how many digits you should round to. The more digits you use, the more accurate you get. You don't have to put them all, and in fact, this particular number never does stop, right? It's a decimal. If we look at all these decimal points, I can't see a pattern. They don't repeat. Okay? So that is one of the properties we'll talk about of this particular type of number in a little bit. But for now, let's just put 19.65. Okay? Let's look at my got it problem. And what is the value of the square root of 34? Now, just off the top of my head, what is the value of 34 to the nearest integer? Okay, so I could use my calculator again and just put in the 34, take the square root, and I can see that it's 5.8. But I don't even need to do that because I know that the square root of 36 is going to be 6, and the square root of 25 is going to be 5. And 34 is closer to 36 than it is to 35. So the answer would be 6. And that's just rounding to the nearest integer. So depending on what the problem says, is the answer could be 5.83 if we want to find an exact answer, or in this case, rounding to the nearest integer, we can round up to 6. Okay, so numbers, our next essential understanding is that numbers can be classified by their characteristics. Some types of numbers can be represented on a number line. We can classify numbers using something called a set. What is a set? Well, it is a well-defined collection of objects. Anything could be a set, but mostly in this class, we are going to talk about sets of numbers. But you could have sets of people, sets of golf clubs, anything, doesn't matter. As long as it is well-defined. You can't really have sets of feelings because they're not really well-defined. Okay, so as long as you can count something or classify it, right, as a well-defined thing, then you can make a set out of it. Each object of a set is called an element of that set. Okay? And a subset consists of elements from the particular given set. So we can break whole sets down into subsets. And we can list the elements of set within the symbols right there, braces. Now, sometimes mine come out very good. Sometimes, if I go too fast, they come out a little wacky. Okay, so just bear with me if we make some set braces. Now, within our number system, there are a few different sets that we can classify numbers into. The first is a rational number. A rational number is any number that we can write in the form a over b as a fraction. Okay? Where a and b are integers, and b is not equal to 0. Because if we put a 0 on the bottom of anything, it is not defined. So, as long as a is an integer and b is an integer, and we can write this as a fraction, it's a rational number. If it's a decimal, a rational number in decimal form is either a terminating decimal, like 5.45, or a repeating decimal, like 0.4166666666. That's what the dots mean. It keeps on going. They're called ellipses, and it just means they keep on going forever. Those sixes keep on going forever. And we can also write that with the little bar on the top. Okay? So if you see that bar, that means that that particular decimal repeats, which means that this is a rational number. Inside of rational numbers are a few different subsets. Okay? We have natural numbers, which are the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No decimals, no fractions, starting at 1 and going up. The only difference with whole numbers is that whole numbers includes a 0. Okay? So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? Integers includes negative numbers as well. So now not only does it go up, it also goes down with negative numbers. Okay? So all three of these, natural numbers, whole numbers, and integers, are also rational numbers. So rational number is the biggest sets. Natural, whole, and integers are subsets inside of rational numbers. If we have rational numbers, we got to have irrational numbers. So irrational numbers cannot be represented as the quotient of two integers. In decimal form, irrational numbers do not terminate or repeat. So some examples would be something with a pattern like this that has 1 0, then 2 zeros, and 3 zeros. And these ellipses means this pattern continues. It doesn't mean that the 1 repeats. If the 1 repeated, it would be a rational number. Also, symbols like pi, which is that symbol right there. There's others like phi, like e. Probably won't hear about those again for a while. But numbers like pi, which are a decimal that never repeats, is an irrational number. Also, square roots are some square roots are rational numbers, some square roots are irrational number. If you have a number that is not a perfect square, its square root is irrational. So basically, if a square root works out, like the square root of 4 or the square root of 25, then it's rational. If the square root doesn't work, it's irrational. But all of these are real. All of these are the set of real numbers. So real numbers include rational, natural, whole, integers, and irrational. Okay? All of those are types of real numbers. Now, because mathematicians are kind of lazy, we have some symbols to represent all of these things. Okay? So the first one, real numbers, looks like that, kind of an R. And whenever we abbreviate a set with a letter, those letters are going to be capital letters. Okay? But the real number symbol is the only one that's a little unique, and we usually put two sticks next to that. Okay? I will show you the rest in a second. Okay? So, to which subsets of real numbers does each number belong? So first, 15. Well, we have to think about it. What is 15? Well, it is part of this set because if we keep that going, it is a natural number. So 15 is natural. It is also a whole. It is also an integer. It is also a rational. Okay, it's all those things. And of course, it is also real. All these numbers are actually real. So we have natural, whole, integer, and rational. Because it has no decimals, it's one of the counting numbers. That's what makes it natural. It's also part of the set of whole numbers, right? The only number that is whole but not natural is 0. Okay? It has no decimals, mistakes, so also an integer. And if I wanted to, I could write it as a fraction, 15 over 1, and that makes it rational. Okay? Number B is negative, so that means it can't be natural. It has decimals in it, which means it can't be whole, can't be an integer. My only decision is this rational or irrational? This one is rational because it stops. Okay? It is a decimal that stops. If it didn't stop, it would have ellipses like that with no particular pattern going on. Okay? However, the square root of 57, I can check that if I'm not sure, but I am sure it doesn't work. Look at all these decimal points right there. Okay? So the square root of 57 is irrational. Irrational. Let's look at a few more. Am I got it problems? Okay? Now don't be fooled with A. It's a square root, but the square root of 9 is 3. So we have to simplify things first before we start classifying them. Okay? So to what set does this belong? Well, because it's actually a 3, that is natural, whole, integer, and rational. Okay? 3 over 10 is a fraction, so it is not natural, it's not whole, not integer. Okay? These 3 right here, no fractions, no decimals. Okay? So it is rational because it's a fraction. This one, part C, is rational because it's a decimal that stops. It doesn't go any further. Okay? And I can tell it stops because the authors made it stop. Now, it wouldn't stop if it had ellipses on it. Okay? But they'd make that clear. And, whoops, sorry. And the square root of 12 is irrational because the square root of 9 is 3. The square root of 16 is 4. So it's somewhere in between there. If I needed to check, I could do it on my calculator and see that it does not work out. Okay? So that is irrational. Now, here's a nice diagram to show you how each set falls into each other. All 3 of these right there are natural numbers because they are 5, 7, and 2. No fractions, no decimals. That is a whole number because 0 is the only whole number. But all the numbers in here are also part of the set of whole numbers. And all the whole numbers here and all the natural numbers are also integers. And this is not a fraction. It's not a decimal. It is -2. This is -5. 4, right? The square root of 16, and then I make it negative. Now, all of these numbers, all the integers, all the whole numbers, all the natural numbers are also rational numbers, fractions and decimals that repeat, or square roots that actually work. Okay, the square root of 0.25 is 0.5. Okay, so that square root works and it stops. All of these rational numbers are separate from the irrational numbers, which are decimals that are radicals that don't work, decimals that repeat and have no pattern, no repeating pattern, and symbols that represent numbers. Now, back in these questions, I kind of wish I had some nice other abbreviations so I didn't have to write out all these words like I do for real. Okay, well, natural, and remember these are going to be capital letters. Natural is easy because it starts with an N. So the set of natural numbers is going to be a capital N. Whole numbers is easy because it starts with the W. So these are going to abbreviate with a capital W. The other ones get a little complicated, okay? Irrational numbers, we can say that is a capital I. But if we're going to use a capital I for irrational, we have to use something else for integers. We can't have two sets with the same capital letter. So the capital letter that we chose to use for integers is Z. Why Z? Because I was taken. And the same thing with rational. We don't want to confuse rational and real, so we have to use a different letter for rational, and the letter that we use is Q. Okay. So these capital letters can represent the sets if you want to not have to write out the whole word. So we could put N, W, Z, and Q for all of these sets. Probably on your homework they're going to ask you to put in the whole word, but it's always good to know, and especially when you get to Algebra 2, it's always good to know these sets. When we are describing them, we don't have to write them out the whole time. Okay, so the next thing we're going to talk about is inequalities. An inequality is a mathematical sentence that compares the values of two expressions using an inequality symbol, of which there are these four. Okay? Less than, greater than, less than or equal to, greater than or equal to. Okay? And when we're trying to remember which one goes which, right, we always read left to right, okay? And the arrow points to the smaller side, and the mouth, I like to think of, I don't want to mess this up. Oh, that's a terrible Pac-Man. But you think of Pac-Man eating up all the dots, and that he always goes towards the greater things. He always wants to eat the bigger thing. Sorry, bad picture, but if you remember that, that's good. So, what's an inequality that compares two things? Radical 17 and 4 1/3. So, when we're trying to compare numbers like this, it's probably best to put them in the same terms. And usually, the most convenient way, to do this is to change them both to a decimal. So we can calculate radical 17, which I should already kind of know is going to be a little bit bigger than 4, since the square root of 16 is 4, and it's going to be 4.123. Yeah, 4.123. And 4 1/3 is going to be 4.3 repeating, 4.333. If I'm not sure, if I can't remember how to do that, we can always, on my calculator, take 1 divided by 3 and add 4 to it. And we get 4.3 repeating. Okay? So if I wanted to compare these two, I can clearly see that this is smaller than this one, that radical 17 is smaller than 4 1/3. So I can say that radical 17 is less than 4 and 1/3. And I didn't have to use less than. I could also write less than or equal to. It's not equal to it, but it is less than it still. So I don't have to be too specific with those symbols, unless we have something that are equal. Okay. Let's do that again with our got it problem. What's an inequality that compares the square root of 129 and 11.52? Well, it's nice that 11.52 is already a decimal. So all we do is take the square root of 129, whoops, not 1,000, 129, take the square root of that, and I get 11.36. So that is 11.36. And we can clearly see that the square root of 129 is less than 11.52. Always best when comparing something to put them to decimals, right? To put them to the same thing, and usually decimals is the most common way to do it. Is there another? Okay, so part B says, in problem 4, is there another inequality that you can use to write that compares the two numbers? Sure. We can say less than, or we could also write less than or equal to. Okay? So either one would work. Next, we can graph and order all real numbers using a number line. So we have graphing and ordering real numbers in problem 5. So what is the order of square root of 4, 0.04, negative 2.3, or negative 2 over 3, square root of 2, and negative 1.5, from least to greatest? So before, we're not just going to guess, okay? The first thing we're going to do is we are going to figure out what all these things equal. Square root of 4 is going to be equal to 2. Okay, we're going to put these into decimals. Oops. 0.4. I don't need to change that to a decimal. It already is a decimal. 2 negative 2 over 3. Well, let's put that into a decimal. 2 divided by 3 is going to be negative 0.6666. Repeating. Okay. Radical 2, the square root of 2, is 1.414. So that's 1.414. And negative 1.5. Okay. So I want to order these from least to greatest. Well, let's put some numbers. Let's label our number line right here so I can graph these later. Let's label this negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. Okay. Negative 1.5 is going to be halfway in between negative 1 and negative 2. Okay. And that's going to be my first one. So I can get rid of A, I can get rid of D. Next, this is the only other number that's negative. And it goes right a little more than halfway. So right there. Okay. So it's clearly my answer is going to be C. But let's keep going. 0.4 is going to be a little less than halfway between 0 and 1. 2, oh no, next is 1.414. So radical 2 is going to be about right there. And then finally 2 is going to be right there. So we can put all of these things on a number line and figure out where they go from least to greatest. Now, of course, we should label our number line way better than I did. Okay, so we should say this is negative 1.5 and so on, just to be clear. Let's try another one. Let's try a got it problem. Okay, so graph my numbers from those numbers on my number line, and what is the order what is the order of the numbers from least to greatest? So let's do the same thing. 3.5. Well, let's put some numbers on here. Negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. This seems like it's going to be the biggest, but let's check. Okay, next we have negative 2.1. The square root of 9 is 3. 7 over 2 is going to be 3.5, and it's a negative 7 over 2. So that's going to be negative 3.5. And the square root of 5 is going to be 2.24. 2.24. So these are the numbers I have on my number line. So we have 3.5, going to be there. Negative 2.1 is going to be a little bit to the left of negative 2 because it is smaller than negative 2 on my number line, right? And as we go left on the number line, we get smaller. As we go right on my number line, I'm going to get larger. So 3 is going to go right there. Negative 3.5 is going to be halfway in between negative 3 and 4. And 2.24 is going to be right about there. And those are the numbers from least to greatest. So least would be this, then this one, then this one, this one, then this one. Least to greatest. Now something we'll talk about later is you should see that the distance from there to there and the distance from there to there are the same. And the only difference between those two numbers, 3.5 and negative 3.5, are their signs. And we'll talk about more about what that means later. So that's the end of this section. Our lesson check, you should name the subset of the real numbers to which each belongs. So you should know that that is a irrational number and that is an integer. Right? You should be able to order numbers from least to greatest. If a square card has an area, length times width, of 15 inches squared, okay? So when I have a length with a unit squared, right, in order to do that, I'm going to find the square root and use the calculator. What are the two subsets of real numbers that form the set of real numbers? Well, that's a tricky one. So if we put two sets together, we would get every number if we put together all the rational numbers, because that's all these, and the irrational numbers, that's all these. So if we take all the rational numbers, there we go. If we take all the rational numbers and we add in all the irrational numbers, we would get all the real numbers. Even though you can't really say it like that, there's a fancier way to say it, but that's the idea. Given an example of a rational number that is not an integer, well, that's going to be anything that has a decimal in it. And rational, irrational. Okay. So that is 1-3, real numbers and the number line.